good morning. So my name is Sunuk Kim. So first I will introduce our team members. From ISE, Dr. Sol Lim is here, Dr. Nosbaum is not here this morning. And from mechanical engineering side, Dr. Dylan Lossi. The effort instead of him is Josh is here to present. And Ivan Hernandez from psychology department. So the topic we would like to talk about this morning is the human-robot collaboration, which is not new. Much effort has been made to enable the effective human-robot collaboration in the workplaces. Our interest is in the specific type of collaboration that involve the multiple human workers. In the workplaces, some tasks that involve multiple team members, especially the tasks that require the high skill and require high skill and the knowledges, such as maintaining, repairing, or producing the highly customized devices. But coordinating the presence of the multiple team members can be very challenging due to geographical constraint or time constraints, and also shortage of the skilled workers. So our question is, if when we try to coordinate the multiple team members, especially the team member has expertise, having them in the place that we want at the time we want can be very challenging. What if the expert is not available? The question is it feasible to the remote expert can work with on-site workers as a means of by manually operating the teleoperator robot to collaborate with on-site workers? So basically, we try to understand how the teleoperation can help with to overcome the geographical constraint and time constraints. Oh, so I had one more slide. Okay. So interestingly, there's a large body of the literature on the teleoperations, but there's a notable gap in the literature that looking at the collaboration between the human on-site workers and the teleoperated remote operators using the robots. So given the lack of the literature, so we look at the literatures. We structure our work in the 3 phases. First, we want to talk with an industry expert to understand their perspectives, and also given the lack of the existing knowledge, we want to set up the test bed that we can explore different scenarios of the collaboration between humans, on-site workers, and teleoperators. And also, we want to develop the specific algorithm that will help to enhance the collaboration between the on-site workers and the remote workers. So we talk with the industry expert. We talked to 13 experts in the industry, from the safety robot manufacturers, automotive, aerospace manufacturers, and supply chains. So we talked with them to learn about their perspectives about the human collaborations. So the findings just published in the recent special issue led by Dr. Lim in the occupational IIE transaction on occupational ergonomics and human factors the papers. So I'm not going to go all the details. We found some the important themes. 13 themes are identified, but we grouped into the 3 topics: benefits and concerns and the technical challenges. One interesting point is the safety and trust belong to the 2 different topics: the benefits and concerns. In terms of the technical challenges, it's a common challenges in teleoperation, but interesting thing is the communications. People think that communication is not just between the human and human operators, it's among the human operators and also including robots, because robot can be intelligent. So we can talk about this graph more, but Ivan will talk more about how we look at the interview data.
Hi, everyone. So yeah, I thought I'd give a little bit more detail about how we can do content analysis on all of this data that we got from these 13 stakeholders. These interviews were really in-depth. They usually lasted an hour, but that also presents complexities, which was a nice kind of product of this research, which is it really serves as the impetus for developing new methods that can better decompose what are the underlying themes within that. So there are already ways to do content analysis. Many of you are probably familiar with this if you've ever done any kind of automated content analysis, but they have limitations. The first is that, like, they ignore word order. You have to relearn the meaning of what a word is every single time you run this. You need these large data sets, which we didn't necessarily have. We had a lot of text, but not necessarily a lot of different, like, stakeholders. There are just many different ways to, like, analyze it, a lot of things, parameters that need to be calibrated, and how many kind of themes there are is a very subjective sort of choice, or what those themes even are is also challenging. So for this project, we developed a new method that was based off of sentence embeddings, which is a relatively newer approach in computer science, where rather than have text represented as words, we'll have text represented as a vector of numbers which represent what the meaning is along different semantic dimensions. Hypothetically, it could be like, how positive is the text? How past or present focused is it? Things like that. So you can take sentences like, how old are you? What's your age? And get numbers that are relatively similar to each other and also relatively different to sentences that mean different semantic concepts. What that produces is the ability to see where are there similarities. So you can see things like, how much is this stamp, or what is the price of a stamp? Those group together. Asking how long should cooked tofu be in the fridge, how long does tofu stay good, those group together. But there is this challenge of subjectivity there, where how do we kind of know what something groups and doesn't group? That's where we added in another type of statistical framework called Gaussian mixture modeling, which is just saying that in a collection of data, like we see on the left, we can see that there are points that are just really close to each other in terms of their density, in terms of their properties that they're measured on, so that we can represent these as maybe a collection of different groups that have an underlying center and variability. Those centers represent what the underlying theme is. It's the thing that all those points sort of center around. But usually one limitation with sentence embeddings is that they're extraordinarily high dimensional. You have at least 384 different dimensions. Often these go up into, like, 1,024 different dimensions. And so finding the common centers in that is really impractical, at least like computationally. You do need a lot of data for that. So we can use dimension reduction techniques where on the left we see a collection of points represented in 2 dimensions, but really we can represent the distance between those points within 1 dimension. We only need one single metric to describe those points as they relate to each other. So we can apply dimension reduction to the sentence embeddings of the text, and then apply Gaussian mixture modeling to see what are the underlying centers within those 2 dimensions. Then we also have the ability to examine what is the ideal number of themes, because this is a statistical framework that has likelihoods where we can see how likely the data are produced by the underlying themes that we find. So if we find that in this model we're going to use 4 themes, we can see how well does 4 themes reproduce the pattern of sentence embeddings. If it doesn't do it so well, then we can compare that to 5 different themes. If 5 themes reproduces it better than 4, then we can stay with that. So we actually have statistical justification to be, this is how well this data this is how well these topics reproduce the data. What you end up with is every single document, every single interview that we had, every single response gets a topic assignment in terms of its probability. But what do we do with that? What do we do once we know that this document is assigned to that topic? We can use large language models like ChatGPT to get a collection of documents that have been assigned to the same topic, and then find the underlying common theme there. That solves so many problems that exist within existing topic modeling methods. We can account for word order. We don't have to learn the word meanings within the spot. We can learn it ahead of time with a sentence embedding and then apply that. We don't really have many parameters to calibrate with mixture modeling. It's a very statistically justified approach for optimal topic selection. And we have an automated way that is reproducible for assigning themes. And so that's how we can get 12 different themes, which Sunwook presented, that were, for example, the response to what types of benefits did the stakeholders perceive. So the gist of everything that they said was that we see these themes of time and cost savings, productivity and efficiency, task performance, but ultimately it produces these 3 hierarchical themes that we found that group them all. Next, we're going to have Dylan's lab talk about the testbed.
So So with the insight from the inner view, they're using IBANs or fancy the algorithms. So we learn about the perspective of the human-robot collaborations. So we want to test in the lab. So we developed the test setup to explore the different types of the human-robot-human collaborations. So Dr. Lim developed this task setup. Basically, on-site worker need to complete assemblies using the parts in the red containers. It's just wires and some bolts and nuts and carabiners. We will see the task video soon. So basically, we want to examine the two different types of collaboration: human-robot-human collaboration and the human-human HH collaborations. Human-human collaboration is a typical the remote collaboration. The on-site remote expert give all the instruction over the phone or the videos, talk to the on-site workers to complete the task. Our HRH collaboration, the robot is in between. The robot is on-site and work with the on-site workers. And then or remote expert give all the instructions through the different types of the communication mode, just talking to them or using the robot to complete the actual tasks. So we ran the small test, look at these two different collaboration scenarios. We recruited 16 DIAs, basically 32 participants to complete the task. So and we look at the different type of the independent variables, collaboration conditions, physical difficulty, and cognitive demand. One thing I need to point out is the cognitive demand and physical difficulty was modulated only for the on-site workers. And we measure different the workload and the postural demands. So here is the HRH. Hopefully the video works. This is a view from the remote worker. So remote worker controls the robot to show how to complete the task and the sequence of the work, give all the verbal instruction, and the on-site worker will follow the instruction from the remote worker. Our scenario is assume that a remote expert has all the expertise necessary to complete the task. So they just complete the task collaboratively, and this will be done in an HH condition that there's no robot, just a remote expert give all the just verbal instructions. And I can move to the next slide. Yep. So we measured different objective and subjective measures of workload and the postural demands. We were still working on the processing the data. So here's the one outcome measures NASA TLX perceived workload. You may be familiar with the NASA TLX. It has 6 dimensions. You're looking at the different aspects of the work demands. So this is the outcome from the on-site workers. So when you look at the effort, so on-site workers during the HH, human-human, the conventional collaboration scenarios, the effort level is somewhat comparable across all the conditions. But when you look at the HRH, human-robot-human collaboration scenarios, the low cognitive demand scenarios, we see some the decrease in the perceived effort, somewhat comparable the effort level during the high cognitive conditions. Here the red color is female and then the blue is male. And when you look at the frustration, so frustration is the perceived frustration or the perceived insecurity during the task. The on-site worker felt more frustrated in the HH condition compared to HRH conditions. And we look at the remote expert, the perceptions as well, perceived workload. Interestingly, during in terms of the perceived effort, the one thing interesting is that during the high cognitive condition, just as a reminder, we manipulated the cognitive load only for the on-site workers. But when on-site workers is under high cognitive conditions, the remote experts had felt more effort. So although they are not, we don't actually manipulate their cognitive demands for the remote expert, still they felt more stressed. It might stress them. And also same for the mental demands. Remote workers felt higher mental demands when the on-site workers going through the secondary task, high cognitive demand conditions. So we still try to understand why this happens. That might be the communication issues, and also there may be a remote worker need to try to understand what's going on with the on-site workers, but we are still working on the analysis. For this test setup, we only, right now, the remote workers 100% manually control the teleoperated robot. This is one extreme of the collaborations. The other extreme of the collaboration can be Josh. We will talk about that the robot has some intelligence to help with the on-site workers.
Hello, my name is Joshua Hogerman. I'm presenting our contributions for this project from the Collaborative Robotics Lab. What we wanted to contribute for this project was if you have these human teams, the robot needs to have some understandings of the task the human will want to go with to help aid the off-site workers for this project. And so what we wanted to do was go over how robots can imitate humans by inferring what the human is trying to optimize for these various tasks in order to assist the off-site human in their replication of these tasks. So one of the major problems we've had for this is that when a robot is trying to infer a human objective, they have to infer over two different dimensions. One is just what is the human going for? What is the theta? What are they trying to accomplish in this task? For instance, are they trying to push the box forward? Are they trying to flip the box on its side? What is the robot looking to accomplish? And then once it has this idea, what trajectory can it go through to accomplish this objective? So in order to accomplish this, the robot needs some understanding in order to judge these trajectories, otherwise known as a normalizer for the statistics it uses to judge this. Typical approaches focus on either just using a very normal uniform distribution in order to judge these tasks. There's also been sampling. For instance, if you take the average completion of this task, sampled over a number of test samples, or using a maximum to judge on a scale of 0 to 1. We went over several of these approaches and found that we could do better. We worked with several of our collaborators in the statistics department to develop a different method using a different approach called the double Monte Carlo method. Using this, instead of just guessing and sampling over a number of different normalizers for the distribution, we instead wanted to have a second internal sampler to add an extra level of variability to these understandings to help them generalize across multiple samples. For the study, we did multiple simulations, which using both off-site generated humans and simulated humans, we found that this method was more likely to give the robot a correct understanding of what the human's tasks were to help replicate and then assist the off-site workers. We successfully were able to approach that this method was significantly more accurate and required less sampling time in order to generate its study. However, to prove these results, we then tabulated it in an in-person user study across 3 separate tasks. The first, technical difficulties. Well, not letting me go back. Just because I'm limited on time, I'm just going to breeze through them. For the 3 tasks, we had one where the human had to collect different pieces of equipment from a box, one where it had to move stuff from this box into different situations in the environment, and then one where the human had to decide on whether it wanted to press a button in order to facilitate this collaboration using the robot itself. Across multiple of these tasks, we found a significantly better human accuracy across the separate methods, and we were able to decrease the time required for these collaborations, as well as the error involved, by a statistically significant metric. But to finish this out, Dr. Kim will go on for our future direction. Oh, sorry.
So this is the last slide, so I hope you are fine. So our next question is like, what's next? So how could we use this type of teleoperation in distributed manufacturing environment to help with the workers, both on-site and also in the remote environment? We showed you one example of most closely like a fully manual robot control that the remote worker is just simply manipulating and operating the robot directly. And then some of the examples of the autonomous robot. And in extreme case, we can even develop this environment into something that we just like talk about some commands like in ChatGPT, like fix A in some facility B, then they could be able to like work on those repairs like in the manufacturing plants. So that's kind of one extreme end of how this teleoperation can go from here, but that's what we are working on, that we would like to like keep investigating from this like preliminary study. So we would like to really thank ICAT for the state grant opportunity that actually led us to get this NSF planning grant in the next year. And I would like to thank our student researchers who put a lot of effort in all of our work. Thank you so much.
Thank you so much. We have time for maybe a question or two. What questions do we have in the room, or are there any online? I'll come to you.
Thank you. Interesting research, very interesting. I was curious about the cognitive demand going up with the computer or robot interaction. Did you look at performance anxiety, and did you look at concern about personal safety?
Thank you. So we didn't look at the particular reason why their cognitive demand has increased, but from our frustration rating, it seems that their frustration level was a little bit higher when the cognitive demand of the on-site worker was high. We are still processing our data, and we also have some open-ended like questionnaire response from the participants that we'll keep working and processing. But thank you for your question.
Other questions? Yeah, I'll come to you.
All right, I'll hold it. Oh, thank you. I have a question more on the method side. So for your content analysis, I was wondering, because usually you identify like 3 or 5 themes from those kind of qualitative analysis. So I was wondering, how did you like cluster the data and come up with like 10 themes?
Yeah. So what was the specific method for determining the optimal number of topics? For this, we used BIC, the Bayesian Information Criterion, and took it at its lowest level across a span of, we started out like looking at from all the way from 2 to 20 topics. And if, for example, like the BIC was appearing like to go lower in that 20 space, we would have increased it. But we actually found the minima at 12. So just relying on empirically what seems to be the topic structure that best reproduces, penalizing for the number of parameters.
Great. Well, we are at time. So I want to thank you all for being here this morning. I think the researchers, you all can hang around for a few minutes if there are additional questions. And I hope you all have a great weekend. We'll see you again next week. And next week, I think we're going to meet the ICAT communications team. So Dylan and Rodney are going to take it away next week. So thank you.